We're going on now to topic 6 of chapter 9, solving exponential and logarithmic equations. And we'll be solving exponential equations and logarithmic equations. So here in this chapter, or in this section, we're going to pull together all of the techniques and strategies we learn going up to this. This is sort of like closure. Solving equations with variables and exponents such as 5 to the x equals 12 and 2 to the 7x equals 64 are called exponential equations. In section 9.3, we solved certain equations by using the principle of exponential equality. So we will go over it below. Now, what does it say? Well, for basically, as long as b does not equal a -1, a 0, or a 1, if we have b to the x power, and that is equal to b to the y power, then we say these exponents are equal to each other, even though they may not look exactly alike, but they are exponents, and they do equal each other. Okay, now let's go on. So suppose we want to solve this one. Well, let me go over it. They give you the details here, but again, I like to help out a little bit here too. So we have 4 to the 3x equals 16. Now you notice here this base and this base are not the same. So the first technique is we have to get the bases to be the same. Now you may know that 16 is actually 4 to the second power. Now that my bases are the same, I can just equate this. And there we have a simple equation. X is going to equal 2/3. And there is our solution. So the key to some that you get like this is to be sure you have the same bases. All right, let's go on. The principle of logarithmic equality for any logarithmic base a for which xy is greater than 0. And the key here, it cannot be a negative number. So it has to be 0 or above. We have that x equals y. And this, by the way, then, is equivalent to the log base a of x is equal to the log base a of y. All right? So let's look at this carefully. And they're also mentioning another important item here. Because calculators can generally find only common or natural logarithms, resorting to the change of base formula, which we had in the previous lesson, we usually take the common or the natural logarithm of both sides of the equation. So the common logarithm is base 10, and the natural logarithm base e, which we also did in the previous section. So here we're asked to solve this. So let's follow their work. I could write it out, but there's lots of writing. So here is an equation. Now notice this is in exponential form. We're going to change this to the log form. So there's our first step, no changes at all. And now we're going to take the log of this and the log of that. Now once we do that, when it's in this log form, we're going to take this exponent and put that exponent, as we had in an earlier lesson, out in front of the log. Okay? Now we have this. Now notice what you can do here. To get this by itself on this side, we're going to divide both sides by the log of 7. Now notice on this side they just cancel out. So we're left with x minus 2, and then we have the division of logs. Now, caution, this is not this minus this. This is this divided by this. Okay. Again, you're going to have to use your calculator. But now to get the x by itself, we're going to transpose that negative 2 to the other side, where it becomes a positive 2. Then, physically in your calculator, you're going to go log, and that's a common log. So you're going to use the log key, 60, divided by key, log 7, enter, get an answer, then you're going to add 2 to it, and you get this. Now, what you should be doing if you are at home watching this, as you look this over, and I'm going to pause my video right now as well to try this on a calculator. And I just did, and we do have an answer. Now, if you take this and put that where x is, and you subtract 2 from it, and then go 7 caret, which will be 2.1041, you don't even have to put the negative 2 there because you already subtracted that. You have an answer. Now, another thing to note is that this is the exact answer. This is an approximate answer, close enough for our work in math. Okay? Now, you might say, do we have to bother to check these? And the answer is probably a good idea, because down the line, some of the answers you're going to generate do not give you a correct equation. They don't check. So for those, we either don't use those solutions, and if there's not another one that we can use, there would be is not possible or is no solution. Something to keep in mind. Okay, let's go on. Now, again, you might say when, and I probably should have said this much earlier, when do I start doing the practice problems? Well, depending, you can start the chapter and start the section, and depending how many sections, if you think you're comfortable with it, that's your practice. Normally in the textbook, they would be giving you examples to try, like if we were using the textbook, they'd say, try example 17. Okay, let's go on. I want to be sure. Now, as we go on to example 3, solve this, which is e to this power equals that. So for this one, we're going to use natural logarithms because of the letter e. So all we need to do up here and over here is stick in the natural logarithm sign, and this equals the natural logarithm sign there as well, and we can put a little e there. Let's see if I can make a better one here. Now notice you have your base, in a sense, identical. So you can, in a sense, say that this is equal to this. Now, what is the natural logarithm of this? Well, your calculator is going to tell you that. And in order to get t by itself, you're going to divide both sides here by 0.06. 0.06, they just cancel out there. Now here it's critical that you all be dividing, but this is the natural log of this divided by a number, not a log or a natural log. Again, this is the exact answer. And when you put it in your calculator, you get this. The technique we're using from a previous section, by the way, is this right here, where we have log base a of a to the k power. This here, remember, was a 1. So whatever was that exponent is this value here. And that's what we're using here. Okay. Let's go on. Okay, here's a little summation of the rule. Well, you can kind of read it over as I do too. To solve an equation of the form a to the t power equals b for the letter t, we take the logarithm, and you can use either natural, the letter e, or common, base 10, of both sides. Use the power rule for exponents so that the variable is no longer written as an exponent. Okay. Divide both sides by the coefficient of the variable, which was the exponent prior to that, to isolate the variable. If appropriate, use a calculator to find an approximate solution in decimal form. Now remember, when we go to the calculator, that's an approximate solution. In its log form, that would be the exact solution. Okay. Some equations, like the one in example 3, are really solved algebraically. There are other exponential equations for which we do not have the tools to solve them algebraically, but we can nevertheless solve them graphically. All right, so solve this and using our graphing calculators. And we will graph this and this to determine any points of intersection. And if you put this into your graphing calculator and you put in, this is y equals 5, which is this blue line, and you use your tracing tool, you can get a point of intersection right there. Okay, we won't have any like this, since again, we don't feature the graphing nature of this. Okay, solving logarithmic equations. Solutions containing logarithmic expressions are called logarithmic equations. We saw in section 3 of this chapter that certain logarithmic equations can be solved by writing an equivalent exponential equation. Okay, again, we're going slow and easy. We're looking at example 5, part A. So we have the log of this equals 3. We'll get to B later. So here's our basic equation. Now what we want to do is change this basic equation into its exponential form. So there's our base 4, which we're going to put right there. There's our exponent that we're going to put right there. And we're saying it equals this. Ah, okay. So we're going to raise 4 to the 3rd power and get 64. And we get this. We're going to transpose the negative 6 to this side, where it becomes a positive 6, add it to our 64, and get a 70. Then we're going to divide both sides by 8, and I get x equals 70 over 8. Now I know I can take a 2 out of each one of these because they're even, and I get this. And you always want to simplify. This is correct. This is in its simplified form. Now we put that back into our original equation, and notice it works out nicely that this is 70 minus 6 is 64, and base 4 raised to what power is 64? Well, it's raised to the 3rd power, so that is true. That is your solution. So let's just look at it again here because we're not in any hurry. We had it in its log form. We changed it to its exponential form. We expanded our base. Now it was a simple equation that we solved. We got this and we checked it. Okay. Now let's go on to B. Now, for example B here, this ln is the natural log. So again, the natural log of 27 equals 5x. So we want to solve for x. Well, we're going to divide both sides by 5. We get x equals the natural log of 27 raised to the 27th divided by 5. And there is your answer. Now I put this in my calculator and I did get a numerical value, but apparently they're saying that is all they want you to do. All right, let's continue. Often the properties for logarithms are needed. The goal is to first write an equivalent expression in which the variable appears in just one logarithmic expression. Then we isolate that expression and solve as we did in example 5. Since logarithms of negative numbers are not defined, all possible solutions must be checked. So what they're saying here is that if you end up with a negative somewhere, like you do down here, depending upon what you get, it may or may not be a solution. So let's do this one here. Log x plus log of this equals 1. And of course these are common logarithms, base 10. So here we're going to take this exponent and this exponent out, and we get our log, this exponent equals 1. Now, what is log base 10? Got to be sure that's in the subscript there. Equals 1. What is that? Well, that is just 10, because 10 to the first power is 10. So that's where this 1 comes in when we think of it from log of what equals 1. It's a 10, 10 to the first. So that's where we got that 10 from, when we converted from this to this. Now, what do? Well, we're going to take this 10, transpose it. We now have a quadratic equation. And this is factorable. It factors into this, which then we use the principle of zero products, and we get these two solutions. Well, let's see then. They're going to give us the check. A -2 and a 5. Now, notice when we plug in the -2, can we have a log of -2? And the answer is no. And we can't have it of -5 either. So this one is false. But plugging in the 5 here gives you a true statement. What is the log of 10? 1. Because this is log base 10 raised to the 10th equals 10. What power would that, I had to cough, so I shut it off. What power would that 10 be raised to give you 10? Well, it's 1. So it does check. And here they're telling you that the number -2 does not check because the logarithms of a negative number is undefined. And on the graph, again, you don't have a calculator, but the graph shows that it only intersects in one spot. Okay? All right, let's go on to number 7. Going on now to example 7. Solve this log 2, which is nice, and this was log 2, so that's good. And we have that. So we know when we have minus from our techniques of logs that we have to divide. So it's going to be log 2, and then since this is minus, this goes in our denominator. So using the quotient rule for logarithms to obtain a single logarithm and writing an equivalent exponential equation. So looking at this, and let's go back and do a little review. We say log 2 of an answer equals the exponent. So this is logarithmic form. What would it be in exponential form? Well, our base is 2 of our exponent, which is over there, and that will equal our answer. So the 2 goes, they're putting it on the other side. The 2 goes there. Our exponent is 3, and there's our answer. They just have this switched around here. Okay. So let's go on. So now what do we do to the 2 to the third? Well, we expand it to 8. And remember, this is 8 over 1. So we can cross multiply, which is what they're doing here. We distribute. We then combine like terms. And we divide both sides here by 7. Transposed, of course, and then x equals 9. And then if we used a graphing calculator, you can actually put this into your graphing calculator, and it shows you this point of intersection right there, which is 9. Wow. So again, it's not until you do the practice and then later the quiz me that you will say you have mastery. And remember, by taking good notes, clear and neat and orderly, that this is available as a reference. You're using a model to guide you to solution, which leads to mastery. And they do the check here, which you'll see in your textbook, and it is true. And in MATLAB, when you put your stuff in there, it makes it true as well. Okay, this one's a little bit different, but let's watch it item by item. So it's the log of this plus the log of that. Now, when you have plus, we're going to be multiplying this. When it was minus, we were dividing it in the previous one. So here we're going to factor out, in a sense, our log 7, and then this goes into a common bracket here, which we're going to FOIL because these are conjugates, and they will FOIL into the difference of perfect squares. And then we do our other side, where this is log base 7. This is log base 7. So we're going to use the principle of exponents equaling exponents. We mentioned this earlier and in other sections as well. So now what do? Well, we're going to transpose that. This gives you the difference of perfect squares. Now we factor that, take each factor, equal it to 0, and we get these answers. Now you then put this -3 into that original equation. And notice here, if that's a -3, you're going to have log 7 of -2. Remember, logs of negative numbers are undefined. So the -3 does not check. That's why you have to be careful. So the only solution is a 3. Now you've done a lot of work. Be sure you don't mess up on your answer by not checking or keeping in mind this statement right here. Okay, let's go on. We wound it up. Now I'm a little bit proud of myself here. If we go back to our start page, this is where I'm getting the multimedia ebook, and I go to my study plan. And this is over Christmas break that I'm doing this. Just taking a moment to come up. It says that I have earned, and I don't know if I showed you one of these a few weeks ago, but I had like only 16 mastery points, but over these days I've earned more. I'm up to 94 now out of 117. I modified the course a little bit since I originally started. So there's a few less mastery points. And as you can see, I have all of section 9 completed. I just have what I just gave you the lecture on. I'll do the PowerPoint, then I'll do the workbook exercises, and then I will do the mastery. And often I will jump right to the quiz bees because I've done the practice already. And these were just other sections that I have not done to leave some blank to show you what it looks like when they're not done. And I should have most of this finished by the end of Christmas break. So when we go into Math 105 on the 20th of January, this should all be done. And I'd have worked on it, and I see that some of you have started on some of these as well. Okay, this will wrap this one up.